like to start referring to the first graphic that's posted on the computer. And these results show how the growth of clusters of galaxies fits into the grand scheme of exploring and understanding the evolution of the universe. Our universe began about 13 billion years ago in a Big Bang. You see at the bottom the little white puff, which produced a hot soup of expanding matter. Ever since the Big Bang, our universe has been expanding, and as it expanded, the soup cooled to form the astronomical objects that we see today at the top part of the figure. The uppermost part of the figure also indicates a most remarkable discovery. Because gravity is an attractive force, it always tends to pull things together and has a retarding effect on the expansion of the universe. Astronomers expect that as we measure the evolution of the universe closer and closer to the present day, we would see an ever-decreasing rate of the expansion of our universe. However, the flaring at the top of the figure illustrates one of the most surprising cosmological discoveries of recent times. By measuring distances to galaxies using supernovae, astronomers showed that the expansion rate of the universe has not been slowing as we expected. Instead, it has been increasing. We live in an accelerating universe. The idea of the acceleration is shown in the figure with a series of springs. We're now confident in the existence of the springs, the acceleration. But now our goal is to understand the nature and the properties of the universe in his theory of general relativity. He introduced a term which is referred to as the cosmological constant. It's a component of the universe which was truly a constant to the contribution to the mass energy density. Hence its name, the cosmological constant. An equivalent formulation of this agent, the dark energy, possibly responsible for the acceleration, comes from particle physics. Particle physics predicted that even the empty vacuum of space contains energy and hence mass. Either of these possibilities is an explanation for the observed acceleration. Alternatively, as Einstein modified Newton's equations of gravity, so Einstein's equations may themselves require further modification. Einstein's equations apply over a truly remarkable range of environments, including the universe as a whole, supermassive black holes, the stretching of time required to make our GPS systems work, the bending of light by matter and gravitational lenses. But despite all these remarkable successes, conceptual changes to Einstein's vision may still be needed. Discriminating between these various hypotheses for the nature of the accelerating agent, the dark energy, is now one of the major goals of observational cosmology. Previous studies have relied on one particular type of test, studying how the expansion of the universe varies with distance, as has been done very notably with the distance measurements to galaxies using supernovae. But now using the Chandra observations of galaxy clusters, we can now apply a new kind of test, provides new clues to the nature of the accelerating agent. Alexei Viklinin and his team have now studied clusters, which are the most massive collapsed objects in the universe, and studied how they grow over cosmic time. If you start now to the next panel of the displays, structures grow from very small fluctuations in the early universe. These fluctuations are seen, as you can see in the figure here, in the cosmic microwave background maps showing the universe in its very infancy. These very weak fluctuations grow and develop into the massive objects observed in the universe today. The next figure shows several snapshots from a numerical simulation which demonstrates the growth of structures driven by the force of gravity. Gravity slows the expansion and amplifies the very small fluctuations first seen in the microwave background. The bottom of these three snapshots also has a few little arrows. And this illustrates the structure growth and the cluster growth in particular, and how it's really a competition between gravity's pull and accelerated expansion. With clusters, we're exploring the properties of this competition on a new scale, roughly 100 million light years. Basically, as the contribution of dark energy to the total density becomes important, the process of structure growth is slowed. This happened when the universe entered the accelerated expansion phase roughly 8 billion years ago. Clusters of galaxies are the most actively forming structures over this particular time interval, and hence they're critical to studying the evolution of the universe, and they're a prime tool to study the effects of dark energy on the growth of structure. Einstein's equations equated geometry and matter and energy, and to paraphrase the cosmologist John Wheeler, geometry tells matter how to move, and matter tells geometry how to curve. With supernova, we have already studied how matter tells geometry how to curve. Now with clusters, we can observe how geometry tells matter how to move. Now Alexei will come back and describe the results of our experiment.
So I'd like to continue by saying that the main reason we use X-ray observations to carry out the cosmological measurements Bill has just outlined is that this is the best way to study the bulk of the cluster's directly observable matter. The bulk of atoms within the cluster is contained in diffuse gas that fills the space between the galaxies. This gas is compressed as the cluster grows and gets so hot that most of its emission is in the form of X-rays. When we compare optical and X-ray images of galaxy clusters, and an example is shown in the next panel, panel 4, it is clear that the X-ray signal is a dominant observational signature. While in the optical, on the left, we see 100 isolated galaxies. In the X-rays, we see a bright continuous halo that closely traces the distribution of matter within the cluster. Chandra X-ray Observatory provides exceptionally detailed X-ray images of clusters. And in the past few years, thanks to advances in both observational methods and theoretical modeling, we learned how to use this data for accurate estimates of the cluster total mass. The X-ray emission is also so bright that it is detectable from great distances, and so can be used to discover clusters very, very far away, as far as half the size of the observable universe. And what's more, Chandra X-ray Observatory is powerful enough to provide detailed X-ray images and temperatures for these discovered clusters, and thus we can determine their masses. Examples of X-ray images we use in this studies are shown in the next panel, panel 5. So over the years, we discovered and observed this Chandra a large number of clusters, both locally and at high redshifts, and so we now know how the numbers and masses change with cosmic time. In a sense, we determine the evolution of the total weight of the cluster population, and we use this measurement to determine the parameters of the universe. This process is like using the scales. On the left plate, we have the measured weight of clusters. We throw different bits of theory on the right place until the predicted evolution of weight matches what's observed. Our main result from this modeling is that we can explain all aspects of evolution of the cluster's weight only by models with dark energy. The observed rate of change of cluster's weight between 5.5 billion years ago and the present is too slow for exactly what's expected for a universe with a low density of matter and large amounts of dark energy. Through comparison of X-ray cluster data with cosmic microwave background, we also determined the growth of structure between 13.7 billion years ago and 5.5 billion years ago. What we found was that the growth was fast up until 5.5 billion years ago, while it really slowed down afterwards. This point in time nicely coincides with the epoch at which the universe entered the accelerated expansion phase, as revealed by the supernova data. Therefore, we're observing an unambiguous signature of effects of dark energy on growth of structure. This may well be called arrested development of the universe. These results represent a completely independent confirmation of the accelerated expansion. In fact, we can detect the presence of dark energy with high significance by using cluster data only without involving any external information. And it is quite striking to me that by observing growth of cosmic structures, we arrive at the same conclusion as by measuring distances. X-ray observations of clusters constrain gravity and dark energy by a very different technique. As a result, we have a much more complete picture of dark energy properties when we combine all different methods. Think about football referees. They try to take different vantage points to make precise calls during the game, and we are basically trying to take a similar approach in studies of dark energy. Properties of dark energy are conveniently characterized by a single number whose meaning is somewhat like stiffness of a spring. When we combine all distance-based measurements with the cluster data, we find that the stiffness of dark energy is very close, within 5%, of the stiffness expected if dark energy is in fact cosmological constant. The stiffness is right at the boundary between a violent and a more gentle acceleration. What this means for the future of the universe is that the accelerated expansion will proceed forever but will probably not result in a big rip. That is, nearby galaxies will eventually disappear from our sight, but the structures already formed, like clusters of galaxies in our own galaxy, will not be torn apart, not in the near future anyway. Our results also mean that Einstein's equations with simplest modifications, adding cosmological constant, seem to do a very good job in describing how the cosmos works on scales ranging from the entire observable universe through 1% of its size down to tiny scales of our own solar system.